Hi, my name is Leah Richter, and this is my honors college project called The Weight of Water. More specifically, I am synthesizing research done utilizing data from the GRACE project. GRACE is the Gravity Recovery and Climate Experiment, a joint mission created by NASA and the DLR. DLR is the German Space Agency. It stands for Deutsche Sonnenstrom für Luft- und Raumfahrt. And it was initially meant to be a 5-year mission beginning in 2002, and it became a 15-year successful observation of Earth's differential gravity field. So it uses dual satellites to measure differential gravitational pull of Earth's surface, and it was used to create an incredibly precise, unprecedentedly precise map of Earth's surface for gravity anomalies. And so this wasn't the only point, though. It wasn't supposed to take 5 years to create one map. It is actually creating an incredibly precise map on a monthly basis. And with this, you can actually see the changes in Earth's mass at different locations around the world and use this to do research, specifically on changes in groundwater reservoirs, rise in ocean, and changing ice caps. This brings me to my honors project research questions. So what was the initial purpose of NASA's GRACE program, and how does it work? So in this section, I'll explain the details of GRACE's function and how they actually managed to measure gravitational anomalies using satellites. Secondly, how has the data collected across the 15 years that this program was active and the ongoing missions now been used so far? This is essentially my synthesis, the crux of what I've been doing, of the studies that have utilized GRACE data for a myriad of purposes, and you'll see that soon. So, and finally, what are the possible applications for the current data going forward? The data as it is has barely been utilized, and what would be interesting concepts to use it for in the future is what we're essentially going to talk about. So without further ado, how does GRACE work? As I said before, GRACE was launched in 2002 to more accurately map Earth's gravity field. GRACE is a twin set of satellites that follow each other on the same orbital plane, approximately 220 kilometers apart. While they're in orbit, they measure several things, including the distance between the satellites, the non-gravitational accelerations like atmospheric drag, and they have precise GPS location, which can be given down to the centimeter. Here we have a diagram of the inside of one of GRACE's satellites. So while there's a lot of instrumentation here, I just want to point out the important parts, namely the KBR assembly, the K-band horn, the USO. These things are used as the microwave emitter and sensor system that measures the distance between the satellites. So they emit a microwave and they also sense a microwave from the other satellite that allows them to, with great precision, to determine how far they are from each other. This is essential because determining the distance from each other is how they detect gravitational anomalies. Now towards the center there's the ACC, the MTE. These instruments are the ones used to correct for non-gravitational anomaly changes in acceleration, such as atmospheric drag. And finally, all of the GPS, the double antenna, all of those are used to record with great precision the location on Earth where there is a gravity anomaly when one is detected. So in this second image, we have this greatly exaggerated image of GRACE's measurements of Earth, but it is used more to highlight the configuration of the satellites. So the satellites are in orbit approximately 220 kilometers apart, one following the other, and they work together to measure gravity anomalies. So how do they work together? When there is a gravity anomaly, such as passing over something of great mass like a mountain range, the first satellite will be pulled slightly towards the Earth. This minute change in distance between the satellites is recorded by the microwave sensing system. And if the second satellite passes over that point and is pulled in the same place, that is noted by the GPS system, and you have detected a gravitational anomaly. So why does this work? Well, gravity is based on mass, and Earth's surface is not a uniform, featureless surface. There are mountains, oceans, and deep trenches, as you can see in these photos, all of which have different crustal mass and density. These differences in mass lead to differential gravitational fields at different points on Earth's surface. In most sciences, however, we use something called the geoid, which is a hypothetical, featureless, perfectly uniform spherical Earth in order to do gravitational calculations. But in fact, Earth's gravitational field just doesn't behave that way. Mapping these differences gives a much better perception of Earth for various environmental and atmospheric models. These features, mountains and oceans and trenches, they stay the same, however, on human timescales, and GRACE is supposed to be a monthly measure over 5 years. So what could we possibly measure that would have a significant change in mass in the surface over that kind of time scale? In one word, water. Groundwater, ice sheets, glaciers, snowfall in the Arctic, ocean height, all of these reservoirs of water are changing on seasonal and annual bases, and now more rapidly than ever, they make up significant measurable mass that is relatable to gravity and therefore can be detected by GRACE satellites. So finally we come to the crux of my project, namely reviewing papers in the following 4 categories that have been used and continue to use GRACE data. As you can see, there are papers ranging from the initial launch of GRACE in 2002 to many papers published this year or very recently, again reiterating that there is mounting potential to use this data for future research. But the categories, the simplified categories, are as follows. We have 3 papers concerning Arctic and Antarctic water storage and ice sheet mass. There are 2 papers concerning groundwater storage in basin and aquifers, 2 papers concerning soil hydrology, and 2 more papers concerning ocean mass change and salinity data, and that's ocean salinity data. So first of all, we have Arctic and Antarctic water storage and ice sheet mass. The first study here is Wally et al. 2021, compares altimetry data with GRACE gravimetry data and reconciles the two to find the mass balance of the Antarctic ice sheet. So altimetry data ultimately measures volume of ice, and gravimetry data measures the mass. Bringing those two together gives us more accurate models than we've ever seen before. And so what we have on this image on the left here, these are 3 different models, Ivins, Whitehouse, and Pelletier, in which red is the loss of ice, as we would expect from global warming oceans. But we also see some buildup of ice in the center of the continent. We would never be able to tell this without the remote sensing data, as these are just really harsh conditions that are very rarely studied, the middle continent of Antarctica. Changing over to the Arctic, Barangi et al. In 2019 looked at GRACE as a correction factor for previous precipitation models in the Arctic. So previously there had been contending sources recording precipitation in the Arctic, but they would often have up to 50% differences from each other, and that was usually thought to be about snowfall undercatch, which was essentially measures of precipitation that were recorded once and then recorded again because they were undercaught and they never melted. And by bringing in GRACE and watching this mass balance change, you could correct for that, and they in fact did. Finally, Frappert et al. In 2009 used an inverted GRACE geoid to track land water and snow mass change. So essentially during the winter they would use the mass change over land and record that via GRACE, and then they were able to track that water's migration into major water bodies during summer, and they did that during the initial GRACE mission from 2002 to 2007. Moving on to groundwater storage in basins and aquifers not in the Arctic and Antarctic. We have the next two papers. They actually read a lot like Barangi and Frappart. Macedo et al. In 2019 actually utilized GRACE data to measure the stream flow recession in 12 different subbasins of the Mississippi River Valley. So the Mississippi River Valley is actually what's shown in this image to the left here. And as you can see, there are 12 dots. Those dots represent stream flow gauges. And so using GRACE data to ultimately look at total groundwater storage, which is the terrestrial water storage anomaly, TWSA, which has a resolution of about 200,000 kilometers. That sounds not great, but it's actually pretty good for a basin of this size. And so measuring the actual stream flow versus these changes in total terrestrial water storage over many months, you can actually determine whether or not there is recession in all of these different subbasins. So Rodell and Famiglieri, 2002, this study was a very important one as it is cited by many afterwards. It was one of the initial studies to use GRACE to monitor declining groundwater storage in the High Plains Aquifer. The High Plains Aquifer covers a lot of the central U.S. states, and it's used to irrigate a lot of our agriculture. So this study was one of the very first studies that used GRACE and gravimetry data to determine how much of the mass of this aquifer was actually being lost on an annual and seasonal basis. So groundwater comes in many forms. It's not just in rivers and aquifers. It also comes in soil moisture and soil hydrology. So these two papers look at soil hydrology, one in the remote area of the Amazon and one of them in more domestic and agricultural areas of Australia. So Massoud et al. 2021 actually used GRACE measurements to improve data fidelity of a previously used land surface model in the Amazonian, a few Amazonian river basins. So with GRACE, he determined total water storage in these areas and was able to incorporate this into the previous model to create an accurate simulation of changes in soil hydrology from 2003 to 2012, which included two major droughts in South America in that time period. Tang Dem Rong Sub et al. In 2018 used similar measurements from GRACE, taking total water storage from Australian soils and using it to correct a model previously used, and that's what you can actually see below here in this image. You can see corrected models. There's the ITSG, the GRGS, which is integrated, and then the MASCON, which is primarily the GRACE model by itself. And then by incorporating these other things, you actually get a highly accurate increase in water storage in centimeters per year along the East Coast and a decrease on the West Coast in Australia. Using GRACE to improve these models can really only help us better understand water cycles as a whole, which is what we want. So finally, we come off of terrestrial models and we look at the uses of GRACE data to evaluate ocean mass changes. So Pont et al. Actually looks at ocean salinity as an average, even though it does vary across the world. We're looking at it as an average. And so the growing input of water to the ocean from sea ice has caused a shifting salinity. And in trying to quantify said change in salinity, the loss of continental fresh water in river discharge and sea ice are both major factors. And so GRACE, the measurements given by GRACE can actually give detailed measures of river discharge and loss of terrestrial water, and therefore inform ocean salinity models. Chin et al. Actually looks at increasing fidelity in global mean sea level change. And so Chin et al. Actually uses altimetry data as well, and it looks at it in concert with Argo floats. Argo floats are physical floats on the ocean's surface that are used to measure the changing height of the ocean. And so as you can see in this top model, there is a weird lag between the Argo floats changes of water level and the change sensed by altimetry. But by bringing in GRACE data along with the altimetry, you can actually line these up and fix that lag that was in his previous model. As you can see, the GRACE data gives context and larger accuracy to many previous models, from ice loss and growth, terrestrial water storage, and mean sea level changes. And although it has its own improvements to be made, it is a new must-have measure in the world of hydrological modeling. So since the initial mission of GRACE was curtailed in 2017, October 2017, they have actually launched a new set of twin satellites on a mission aptly named GRACE FO, FO for follow-on. This mission was launched in May 2018, and it carries new, even more precise measuring systems, including a new accelerometer, a microwave transmitting system accurate to several microns thick. That's about the thickness of a blood cell. And they are testing a laser light system designed to be even more accurate than the microwave transmitting system. So what kind of information might we learn and might we want to know as GRACE FO gives us more information? What are possible applications for current data and ongoing research? Arctic and Antarctic water cycle changes affect global water cycle changes. And so permafrost thaw and drainage, ice sheet loss or growth, and glacial loss all affect the global water cycle and can be tracked through remote sensing. Groundwater storage is incredibly important for developing and industrializing nations. Depleting globally important aquifers can actually lead to major problems with the populations that depend on them. Finally, sea level rise is coming and will be an important issue with global warming and will disproportionately affect some global communities. And therefore, being able to track it with as much accuracy as possible is very important. I just wanted to thank you all for listening. Enjoy this map of GRACE data and the gravity anomaly. But just wanted to point out that for every utilization highlighted here, there are at least a dozen that have not been highlighted and that can be used and should be used to give us more information about the Earth's water cycles.